We're going to continue building on our knowledge of atomic structure now. I really like this animation. One of the things I love about it is that it kind of incorporates all that element symbol stuff that we were talking about. It's got mass numbers, atomic numbers, and this is actually the charge area, which we're not going to worry too much about in just a second. But another thing I like about it is we can kind of build a bunch of different elements by changing the number of protons, right? So that should make sense. So if we grab this little guy and put it in there, notice that that kind of is a really good visual of recognizing that a single proton, right, means that it has to be a hydrogen. And then we could kind of keep going and we could build a helium, right? And notice that you're kind of doing that typewriter thing, assuming anybody knows what a typewriter is anymore. But as we kind of keep adding more and more protons, we're kind of working our way across the period. And so that's one of the reasons that when we look at the periodic table, we notice that atomic number is so important because it gives the identity to the element. So another thing which we can see here is that, first of all, this is incredibly unstable because we don't have any neutrons to kind of keep those protons together. And you'll kind of notice here that it shouldn't be surprising, since protons are positive, that we have an overall +3 charge. So we obviously need to add something, right? And actually several different things. And first of all, we're going to add neutrons just to kind of see what it does to the mass number. And you'll notice that each time I do that, I actually end up with, let's say, a lithium 5. Now I can add another neutron, and it's lithium 6. And then I could get to the most abundant isotope of lithium, which is a lithium 7. So hopefully this will kind of help you to understand that idea of isotopes. Also kind of see the difference between mass number and atomic number, right? If I want to take out a proton, you'll notice it becomes a helium. If I want to add one, it becomes a lithium, et cetera, et cetera. I'd really recommend you guys play with this a little bit. It'll definitely help you to understand the connection between atomic structure in terms of the actual model of the atom and those crazy numbers that we're using. We're going to build on this model a little bit now, though. As before, we just kind of, for a lithium atom, we would just kind of blindly throw in 3 electrons. But an interesting thing happens when we try to put those 3 electrons in there. Well, obviously, if you take a look at this charge, every time I do that, the charge changes, which should kind of make sense. So here now we're at a 0 charge. But one of the things you'll notice is that these electrons kind of seem to be orbiting differently. For whatever reason, I put 2 electrons in this kind of lower level here, and there wasn't enough room in that lower level, and I suddenly had to put another electron out on kind of the periphery of this atom. So this gives rise to all kinds of important things, most of which we'll talk about next week, thankfully. But the one thing we do have to talk a little bit about, at least in a kind of a pretty fundamental level, I'm not going to go really into the weeds here, is, why this is happening. What are these shells about, and how can I use the periodic table to predict this? One of the things that you'll notice as I kind of go back here, so notice that the first 2 electrons always go into what's called the first principal shell. And curiously, there seems to be a little bit of a correlation between the amount of electrons you can put in a shell and the kind of width of your, I shouldn't say width, but the number of elements that are in your period, right? And so here's the first period. First period only has 2 elements, hydrogen and helium. And it turns out that this entire table is organized according to electronic structure, right? And so those 2 electrons right there, I'm essentially starting at the first period every time I have to put electrons in something, and I'm going 1 electron, 2 electron, and when I kind of press the return key on the line or the typewriter, if anybody knows what the heck that is, that actually tells me that I have to open up another shell. And so a lot of the next PowerPoint is going to describe some of this stuff. So that very next electron, because I'm in this very particular region right here, right, I have to get to lithium. It turns out that I have to open up an entirely new principal shell. So the shells of the atom roughly correspond to the the number of your row. This is kind of a weird thing. So we're going to develop this a little bit in a second here. And I really encourage you, once we've had that discussion, to kind of go back to this thing and see different fun things you can do to understand atomic structure, and specifically in this case, electronic structure. So electronic structure really looks a little bit like shells, right? And so what I've done here is this is just kind of like an idealized atom, right? We've seen this a bazillion times, right? We're kind of peering inside of those spheres from the particle diagrams now. We know about the middle of an atom. We know about the nucleus containing protons and neutrons. But now what we're going to do is we're going to start to talk a little bit about how you can understand the electron orbits. And it turns out the number of electrons really gives rise to all the important things in normal chemistry, right? It's the reason that things react. It's the reason that things bond. So it's a really central concept. Unfortunately, because electrons and atoms are so small, there are some really odd kind of quantum mechanical rules. So we could really get lost. Like we could literally talk about this all year long and it would still be confusing. So what I'm going to try to do for you is just kind of do my best to do kind of like a brief overview, show you how to do a couple of things that can impress grandma or people in your house. Waldo the dog probably won't be impressed by it. But we'll get you to kind of a conversant level a little bit here. So first thing to recognize is that electrons live in kind of an apartment complex, right? There's some electrons that live on the first floor of the apartment complex. There's some that live on the second floor, and some that were kind of live on the third floor. These are all called principal shells, right? And these principal shells really roughly correspond to the rows on the periodic table or the periods of the periodic table. So that's kind of a concept we're going to develop as we go here. The really confusing thing happens in that this apartment complex is totally bizarro. You've got an apartment complex that, has like the first floor, right? The first floor is kind of the closest one to the nucleus, right? And so you can kind of imagine electrons living on this floor of the apartment complex. The problem is as you get farther and farther away and kind of like bigger and bigger shells, what happens is you get kind of like sublevels, right? Well, they call them sublevels. It's almost like you no longer just have a second floor. You have essentially two second floors, right? That second floor is kind of split like a god-awful studio apartment like I used to live in, that kind of has a living area that's a little bit lower than, let's say, I don't know, the kitchen or something like that. At least that's the way it was in that god-awful place. And it gets even worse because if you go out to the third energy level, it turns out that this thing will actually split into kind of three sublevels or three floors. Right? And so what happens is that things start to get more and more complex as you go farther and farther away from the center of an atom. And obviously, as you work your way down the periodic table, you have to make room for more and more electrons. And that's kind of why we saw that, as we go down a family, the atom size started to get bigger and bigger and bigger. Okay, shut up, Breslin, and just get on with it. So this guy, this is kind of a representation of a nitrogen atom's electronic structure. Keep in mind that this is awful in that this representation of a nucleus is way too big. They just kind of zoomed in on it, and so that you can kind of see that it was in fact a nitrogen, and it has its well, there's I guess one even missing, but it should have 7 protons there. So we're not going to concern ourselves with this so much, right? We're going to talk about these little crazy things called electrons. And the reason that I include this slide is actually because you can see that the first shell just has that single level, right? It's kind of like a single orbit. But then when you go out to this second shell, right? This is the second shell here. There's actually 2. And we could then go out to the third shell and there'd be 3 different orbits. And then the fourth shell, things get really crazy. There's 4 different orbits. And things start to get really complex really fast here. You'll notice in this representation that there's this little tiny box here that actually turns out to be pretty important. These things that we're going to be talking about are called electron configurations, right? And so electron configurations are a really bizarre way of representing with letters and numbers what the actual picture of the electronic environment looks like. And again, it's because these electrons are so important. And you'll kind of see that a little bit next week. But what we do with the electron configuration is that every time we start putting electrons in an atom, we always start with what's called the 1s sublevel, right? The 1 corresponds to what principal shell you're in, or kind of what major, the shell that you're in. Let's just call it that. So this would be the first principal shell, and these both together would be the second principal shell. A sublevel is something that is kind of the next order of division, right? And so it turns out the good news is if you're in the first shell, you only have something that we call 1s, and it only has room for 2 electrons, right? And so those 2 electrons got put in there because, of course, this is a nitrogen that needs to account for all 7 of its electrons. So what we have here is the 1s2 designate corresponds to the fact that there's 2 electrons in that first subshell. When you go up to the next one, you'll notice here that you always add electrons on the kind of the inside shell first. And the weird thing is that the first thing to fill, the first sublevel to fill in every single principal shell is always of S type. And that S only has room for 2. And this will make a little more sense when I show you another slide in just a second. So S's always have room for only 2. It turns out the next level here has room for 6. And of course, we don't need to put a total of 6 in there. We only need to put 3 in there because we know that we have to put 2 electrons in. We put the 2 in the first shell. We put another 2 in the second shell. That's what corresponds to the 2s2. And then, of course, we have to add another 3 electrons. And so what we do is we put them in what's called a p subshell. Okay, so it's getting weird, I know, and it's probably a lot for a single day, but that's kind of the the place that we're forced to work here. So you would say nitrogen's electron configuration is 1s2, 2s2, 2p3. And it turns out that chemists have been, drinking that special Kool-Aid for long enough that the second you say that, this kind of picture pops up. And it turns out to be important for bonding and such. So just to kind of summarize, right? We're talking about what's called electron configurations. Importantly, you should know that this is a symbolic representation of electronic structure of an atom. And there is an example, right? There's nitrogen. It's got 2 electrons in the very, very first subshell. It's got 2 electrons in the second subshell, and 3 electrons in the other type of second subshell, which is called a 2p. And I know what you're thinking. You're thinking, what the heck do the S and the P correspond to? Do they stand for something? The answer is yes, but it's German. So the Germans have come up with all kinds of different ways of confusing people throughout the ages. But this is all kind of from those days. And they've just kind of stuck with us, right? They could have called it, I don't know, level A, level B, level C, level D, but that's not what they did. They called them S and P, and it has to do with the way that light interacts with matter and all kinds of stuff I don't want to talk about. So let's kind of continue the madness here a little bit. Here are electron configurations of, a couple more elements, right? And you'll notice that chemists have come up with 10 billion ways to show these electron configurations. These are called orbital diagrams. We're not going to worry about those in this version of Chem 112. Be thankful for that. But what we are going to worry about just a little bit are these electron configurations, right? You'll notice that if I'm a lithium, how many electrons do I need? It even tells me right here. Well, I know 3, right? I know if lithium's going to be uncharged, I need to have 3 electrons to balance out the 3 positively charged protons. That kind of makes sense. And so what I do is I start with the 1s level, I add the 2 electrons, and then we just saw in the case of nitrogen at least that then because I filled that very first subshell, I need to stick an electron in that the 2s subshell. Right, you can kind of see the pattern of things here. Beryllium, now we're going to put 2 electrons in there. S levels can only get 2. So you'll notice that 1s2, 2s2 is the electron configuration for that. Because those S's can only hold 2 electrons, once we get to boron, you'll notice that suddenly we have to put this thing in what's called a 2p1, carbon, 2p2, nitrogen, 2p3, neon, we skipped a couple, 2p6, and then all of a sudden we've got to open up a completely different subshell, right? So what I'd like you to show you, right? The first time I saw this, I thought, oh my God, I'm never going to understand this. It's totally bonkers. What all these numbers mean? Well, it turns out that this slide will hopefully kind of help you to see this thing. What we have here is the periodic table without any elements, right? So it's just a periodic table where you can imagine all these elements in here. And what it's done is it's actually labeled each one of the principal shells, right? And also you'll see that they correspond to a row of a periodic table, right? And so this tells us pretty much, let's imagine that we want to go to, let's say, neon. This is neon right here, right? Well, what we do is we always start at the very, very top, and we just kind of count boxes and kind of keep track of what the sublevel is called, right? This very first part of the periodic table is called the S block. The reason it's called the S block is because if you were to end here, right, if you were going to choose an element in the uncharged state from any one of these areas right here, you would always be ending with some sort of S subshell, right? This guy is called the P block, right? These are where you're going to be filling P-type electrons. You'll notice as you work your way down the table that, you know, there's only an S in the first row. Well, now that you're in the second row, now you've got 2 different subshells. You've got an S and you've got a P. You work your way down to the third subshell, sorry, the third row of the periodic table. Now you've got an S, a P, and there's the D, right? That's what the third level is. But there's all kinds of weirdness going on with this this S block right here. And what this kind of shows you is that it looks like electrons fill kind of out of order, right? Instead of completely filling the third subshell right here, you actually fill the third subshell up to the 3p6 level. Then you go down, you fill a couple of 4s's, and then you go back and you fill what's called the 3d, and then you go and you fill the 4p, right? Notice that I'm always starting at the top and working my way down. So that's, you know, that kind of out of order filling has to do with the fact that when you split these floors of the apartment building, some floors kind of get in the way of other floors, and there's all kinds of a mess going on. It's important that you know the names of these things, but I promise I won't ever ask you for anything beyond this point. And the reason for that is that once you get to filling up this 5p subshell level, you fill 2 electrons in S, and then you have to go down here, and then it becomes a 4F, and there's all kinds of like really complex stuff happening. So what we're going to do is we're just going to concentrate on kind of the 5th row and higher. And quite honestly, even within there, there's like kind of weird exceptions. But we're just going to kind of learn something that allows us to talk a little bit about electron configurations. So long story short, let's go back and remember when we were talking about neon right here. Let's say that I had to figure out the electron configuration in neon. Well, what I do is I kind of circle it, either physically circle it on my periodic table, or I just kind of keep that in my mind. And what I do is I count levels and I put electrons accordingly. So in other words, I'm going to go, okay, there's 1s1, 1s2. Oh, okay, so I took care of that 1s subshell, right? I got 2 electrons in there. Now I got to go with the typewriter and go back here. Okay, now I got 2s1, 2s2. Okay, oh, whoops, I'm all done. Fill in my 2s2. I'm going to continue right across the period and say, okay, what is this? Oh, that's 2p1, 2p2, 2p3, 2p4, 2p5. Oh, 2p6. That's where I needed to end, right? And so if you look at the previous slide there, maybe I'll just kind of go back to it, right? If you look at the electron configuration in neon, you'll notice that's exactly what it is, right? It's a 1s2, 2s2, 2p6. Okay. In your lecture supplement, I've included a couple of different ways of understanding electron configurations. We're just going to kind of go through a couple of those. You'll notice here, right, each one of these guys has the blocks labeled, and the one advantage of this particular way of looking at things is that you also have the identity of the elements here. And so, like, there's our neon example, right, and we figured out that, oh, wait, that ends with 2p6. We're going to get a little bit more complex here. We're going to find some electron configurations for atoms that are deeper into the periodic table. And I'm not sure the best way to show you this, so I think I'm just going to show you the way I think might work, and then when I confuse the hell out of everyone, you can just ask me some questions in office hours. Honestly, the kind of give and take of an office hours is one of the best ways to understand this, just because it's so bizarre. So anyway, let's pretend you're in my brain, you poor people, and let's say that I want to find selenium on the periodic table and I want to do an electron configuration, right? Well, it turns out I always have to start here, and you'll notice that I would go 1, 2, right? And so that just filled up my 1s block. So I would say 1s, well, that should be superscripted, but I'm going to not worry about it. Then I would come down and I would say, okay, what block is this? Oh, that's the S. I got space for 1, 2, and it's in the second period. So that is a 2s2, right? And so at that point, I've gotten myself down to that box. I'm going to keep going over here. What subshell is this? Okay, so I'm in the second row. I've got, oh, this is the P block, right? Okay, so how many can I fit in the P block? 1, 2, 3, 4, 5, 6. 2p6 now. Okay, so I've gotten down to there. I keep going. I come over here. What block is this? Okay, it's the third row, and this is the S block. Okay, and I got space for 2. 1, 2. So I'd come up here and say 3s2. I go all the way across, and I'm not there yet. Okay. Oh, the P block again. And I'm in the third row. Awesome. So 3p, how many do I got to go? 1, 2, 3, 4, 5, 6. That gets me to what's called the noble gas core, and that'll become important next week. And now I am at argon, right? It's not argon. I got to go to selenium all the way. So now I say, okay, I got to press enter on the typewriter, go over here. Okay, what is this? Okay, it's the fourth row. Okay, so this is the 4s block, right? So I go 1, 2. So that's a 4s2. I come here, and then I'm like, what the hell is going on? Oh, that's right. I didn't fill the last bit of that 3, right? Oh, now I got to fill the third shell. Even though I just filled a little bit of the fourth shell, I got to switch to the third shell because quantum mechanics is weird and it hates you. Now I'm going to go, okay, well, I just have to remember that this D block is kind of 1 off of the period number. That's weird, but I can remember that, I think, right? All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I filled up all of that. That's called 3D10. And now what? Am I at selenium yet? Oh my God, I got to keep going. All right, so, okay, we got one. Oh, okay, I'm back in P land here. Sorry, I'm a 5-year-old. So I'm in the P block, so that means that I'm in the, let's see, the fourth row. Okay, so that row matches the principal shell number. So I can go just 4p1, 4p2, 4p3, 4p. Nice, I'm done. I stopped at selenium, right? That's going to be a 4p4. Right? And so this thing right here, of course, I should have superscripted all the last numbers there. Keep in mind that's telling me what this selenium atom would actually look like, right? It would have all of these different subshells with that particular set of electrons. And I could keep going, but there's kind of a pain in the butt more than you might think, right? Because wait a second, once you get down to selenium, right, you're really just repeating all the elements that kind of came before them, but just like filling up the rows completely, right? And so this entire part right here up to 4s2, right? So this 1s2, 2s2, 2p6, 3s2, 3p6 is going to be present in everything argon and lower, right? And so, that's called the noble gas core. So what chemists have done to make things even more confusing is instead of talking about full electron configurations, we can then talk about abbreviated electron configurations, right? So the abbreviated electron configuration is, just like we wrote before, is still going to have a 4s2, 3d10, 4p4, but what we're going to do is we're going to put argon in brackets, right? And so if we kind of click back here, remember everything up to this point right here is essentially argon, right? And so what we're going to do, I'll just do a little copy and paste here, I hope. And what we're going to do is we're going to take all of that and we're just going to say, okay, it's a pain to always have to do that. What we're going to do is we're going to put this thing in what's called an abbreviated electron configuration by putting argon in brackets, right? It doesn't tell you that it's an argon, but what it tells you is that the core of electrons is the same for argon up to that point, and then we have to add all this other stuff. It turns out the abbreviated electron configurations always end with a noble gas element, and as I always say, this will hopefully become a little more clear why this madness is happening to your brain hole. Once we get to next week, we'll understand why those noble gases are so important. So looking at this, all these different subshells that exist, you can kind of see this is why the subshells kind of get more and more complicated as time goes on here, or as you get farther and farther out from the nucleus. The nucleus is down here. What happens is that all these levels that split, they don't split entirely equally, right? And so what happens is this cluster at the top where things all just kind of get all jumbled together. Really, if we really cared about every element on the periodic table, you could look at different graphics like this that kind of help you to figure out what the filling is. We're not going to talk too much about it. But what we will do is probably I'll, just as kind of a reward for kind of sticking with me all this time, we're going to see a demo that has to do with why this craziness right here gives rise to some really awesome fireworks. I know you're probably thinking, what the hell does all this have to do with fireworks? Well, it turns out that all of this, if this didn't exist, it would be a really boring world because we couldn't light things on fire and get really beautiful colors.